Today we're going to expand our knowledge on geometric series and talk about infinite geometric series. A geometric sequence has no end, so finding its sum can be a little bit tricky if I'm talking about the whole thing. First, we need to be able to tell if a sequence even has a sum. And what I mean by that is if I take this series, right, 1, 2, 4, 8, 16, 32, 64, and on and on and on, these numbers are going to get infinitely large. The further I go into this series, the bigger my numbers are going to get, until the sum itself is going to get infinitely large, and I won't be able to physically add those numbers together. We're going to say that this type of sequence does not have a finite limit. That needs to go in your notes. We'll explain finite limit in just a minute. If a series doesn't have a finite limit, it's said to diverge, and we can't find its sum. Now, a finite limit means that we're limited to the number of terms we can add together, that I can actually physically add those terms together. So, to diverge means that you cannot find its sum. This will always happen when the numbers get infinitely large. In order for that to happen, the common ratio has to be larger than 1, or I can say smaller than -1. So I'm multiplying by a 2, or a 3, or a 4, or a 7.5. We can simplify this statement by simply saying the absolute value of r, or the absolute value of your common ratio, has to be greater than 1. On the other hand, if the series has numbers that get smaller and smaller, like 12, 6, 3, 3/2, 3/4, 3/8, the numbers themselves will eventually get so small that adding them to my sum won't make a big difference at all. In fact, they'll get so small that if we were talking like a molecule, it would be so small I wouldn't be able to see it with a human eye. So these numbers can get so small that adding them onto the end of my sum won't really make a difference. We can estimate this sum. We're not going to be able to get it exactly, but we can estimate this sum and set a limit to what that sum could actually be. In order for a series to get small like that, the common ratio needs to be between 1 and -1. So for instance, 1/2, 0.01, -2/3, those are all common ratios that will make my numbers get smaller and smaller and smaller. So we can say the absolute value of r has to be less than 1. A series like this, we're going to say that this converges, or it's said to converge or approaches a finite limit. There's a limit to how big this sum can get. So let's take a look at a few of these sums and find out if the sum actually is going to exist. So how about number 1? Are these numbers going to get larger and larger up to infinity, or are they going to get smaller and smaller? In this case, they're going to get smaller and smaller, so this one does actually have a sum. It has a finite limit, so I'm going to say yes, it has a sum, because the absolute value of my common ratio is less than 1. Number 2, take a look at the common ratio here. Our common ratio is 3. So does this series have a sum? Are these numbers going to get small, 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 or are they going to get large, large, and infinitely larger? These numbers are going to get large, right? And I can't add infinity since it's not actually a number. So this one I can't find the sum of, and I'm going to say no, it doesn't have a sum because the absolute value of my common ratio is greater than 1. How about number 3? Does it have a sum? Yes, it does, because our common ratio of 1/3 is less than 1. All right, and finally, number 4. Since our common ratio is -3, right, remember to take the absolute value of that. Our numbers are going to get, they're going to look like they're large, 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 right, but they're going to be negative, so technically they're getting infinitely small, but I still can't add negative infinity. So I'm going to say, no, I can't find its sum because my absolute value of my common ratio is greater than 1. So now let's get down to the nitty-gritty. How do we find that sum? So first, recall the formula for your finite series, right? We had our sum is equal to our initial term times 1 minus common ratio to the power of n over 1 minus r. Well, we're going to do a little manipulation here. So first I'm going to distribute the initial term through my parentheses. Then I'm going to split this into 2 separate fractions so I can put them over their own 1 minus r denominator. And then let's take a look at that second fraction. This fraction, because I'm multiplying by my common ratio to a power, this is the one that's either going to get really, really large or so very, very tiny that it gets so close to 0 it's not going to make any difference to my sum. Well, since if my common ratio is less than 1 and it gets so tiny, that part of my sum I can actually ignore completely. So I'm going to cross it off, get it out of my way. It's not really going to make a difference to my sum if I can actually find a sum. So for an infinite series, I'm just going to focus on this first fraction. I'm going to take my initial term and put it over 1 minus r, and that's going to be my limit. That's going to be my finite limit where my sum can go towards that number but will never surpass that number. Remember that this is only possible when the absolute value of my common ratio is less than 1. So let's try it on our 4 examples from earlier. So let's look at number 1 first, right? We're going to actually find the sum. This was one we answered yes to, that I could find a finite limit for my sum. So I'm going to put it into my new formula, a sub 1, or initial term, over 1 minus r. That's going to give me 4 over 1/2. Remember, to divide by a fraction, we multiply by its reciprocal, and I'm going to get 8. That sum is going to have a limit of 8. It's going to get really, really close to 8. Even if it never actually reaches 8, it's going to be so close to it that we can't tell a difference between the two. Number 2, we said we couldn't find the sum because the sum was going to be so big we wouldn't be able to write it down. So I would write no sum exists because the absolute value of r is greater than 1. Number 3, we said we could find a sum or at least a finite limit. So I'm going to put my initial term 5/2 over 1 minus r, which is 1/3. That's going to give me 5/2 over 2/3. To divide by 2/3, I multiply by its reciprocal, and I get 15/4. We're going to say that that's our sum, or we could call that our finite limit. Number 4, because r was, well, the absolute value of r was greater than 1, we weren't actually able to add these together. So again, I'm going to say no sum exists because the absolute value of r is greater than 1. We can actually use this formula for more than just addition. Remember our repeating decimals, and remember back in It was probably about middle school that you had to change those into fractions. Well, this formula actually helps us change these repeating decimals into fractions. First thing you want to do is change it into an actual series. So I have 0.41, then I'm going to take the next repeated part, the 4 and the 1 here, which is 0.0041. Then the next repeated part, 0.000041, and I'm going to keep repeating that pattern to make this into a series. In order to find R, I'm going to take this series a little bit backwards, and I'm going to take 0.0041, divide it by 0.41, and find that R is 0.01. That's what I'm multiplying by to get the next term in my sequence. I'm going to plug my initial term, 0.41, and my new R, 0.01, into my sum formula. That gives me 0.41 over 0.99. Now, there's two ways to get the job done here. I can simply move my decimal place top and bottom over 2 places. In other words, multiply top and bottom by 100. Or I can change them both into their own individual fraction over 100, because this is 41 hundredths and the denominator is 99 hundredths. Multiply by the reciprocal, and I get 41 over 99. Let's try that again. How about, oops, I think I forgot to change that. Let's do this one. Change 0.256256256256256 and on to a fraction. So again, first we want to change it to a series, right? 0.256, 0.000256, 0.000000256, and on and on and on. Next we need to find R. Take one term and divide it by the term before it. This time I get 0.001 for R. I'm going to put those numbers into my infinite sum formula. Simplify the denominator and I get 0.256 over 0.999. That means 256 thousandths over 999 thousandths. So I could just multiply top and bottom by 1,000 or multiply by its reciprocal, and I get 256 over 999. I do want to reduce this if I can. For now, we're just going to leave it be. Make sure to write down any questions that you have about our new infinite sum formula and let me know in class. See you then and have a great day.